Hello, how are y'all doing? I'm hoping that one of you will indicate that you can hear me.
I can hear you.
Love it. And if the sound gets horrible in the background, please let me know. I could probably adjust things. But right now I'm sort of outside, and if it gets loud, let me know. I'll fix it. So hopefully your day's going well. I've had ups and downs, some of each. Egypt losing in the soccer game was sort of a bummer. Oh well. Not unexpected, but the fact that they were close for part of it really ended up being a bummer. Okay, let's think. What I want to do is start by sharing a screen, and let's see how to do that. Yeah, share screen. Okay, right now, as far as I can tell, you should be looking at um, me and also the screen. And so what I want to do is maybe just sort of start with a couple announcement-y things. One of them is I was looking at the syllabus earlier today with a student who came by office hours, and it seems like if we're lucky, and I wouldn't be surprised if we do get lucky, we'll finish up with the material for the next midterm in class today. So looking at the syllabus, what I'm spotting then is the syllabus says our test starts on Thursday. So we should be finished perhaps with chapter 5 today. If we don't get there, we don't get there. But if we do, that'll give us like a full class session before even the exam is released. And what I'd love to do is to spend a lot of time tomorrow talking about questions from the sample exam. Oh, so you're feeling confident and ready to take the actual exam, which is then on Thursday through, I guess, Saturday at midnight. So you got, again, 48 hours plus a little bit to do the test. And if we are able to get into chapter 6, wonderful. And if we don't, well, that's okay too. The material in chapter 6 is, in my opinion, the lowest import of everything we do this entire semester. That feels wrong to say it that way, but you know what I mean. And so, with all that in mind, uh, if there are questions on even Thursday before our exam, I would rather spend time talking about questions related to chapters 4 and 5, 3, 4, and 5, than moving forward into chapter 6. So, just hinting at something that you guys could do for me tomorrow. Okay, so that's one thing I want to mention. And let's close out of that and maybe pause for a moment. Are there any questions about the date of the exam or past exams or anything like that? Okay, so what I'm going to do is sort of move forward in the material into discussion of yesterday. Yesterday, we gave you some basic probability definitions and rules. Okay. And we got through this general edition and we defined conditional probability, but we didn't quite get to independence. Any questions from yesterday's class or problems that have come up since yesterday's class? Okay, so what I'd love to do is sort of start with independence and then move on into defining a random variable and then get into sampling distributions. And we'll just see how it goes. Should be good. Okay, what do I want to do? Let's do that. And now that we have a blank screen, I can sort of move forward to fill it. So let's remember what we talked about for conditional probability. And here's just one way of phrasing this. You could say that the probability of an event A occurring, given that an event B has already occurred, I could, suggest a time ordering, but it's not required. But it helps to think it through. That's equal to probability that A and B both occur, divided by the chance that B occurs. Okay. So that's conditional probability. Yay. And we then said, well, what about the probability of A and B, the intersection probability of A intersect B? I could write that out as the chance of well, let's back up a little bit. I want to do it a little bit differently. That's the chance of B occurring times then the chance that A occurs given that B has already occurred. No problem. We just multiplied. Or to be honest, I could also write that that's equal to the chance of A occurring times the chance that B occurs given that A has occurred. Either way, okay? But that suggests the following. It suggests, well, we could just multiply those conditional probabilities together to find the chance of the intersection. I'm good about that. But we didn't really talk about one particular special case, and that special case is the case of independence. If A and B are independent events, in plain English speaking, the chance that A occurs doesn't depend on whether B occurs or B doesn't occur, or there's no information about B occurring or not. I could write that the following way. The chance of A occurring is equal to the chance that A occurs given that B has, or like we suggested, it's also equal to the chance that A occurs given that B maybe has not occurred. Me telling you whether B occurs or not has no bearing on how likely A is to occur. That's a special case. And if that special case is true, then I think we can do a little bit of extra work and we can sort of be happy people. If A and B are independent events, we know that A occurring, the chance of that just doesn't depend on whether B occurs or not. So what if that is true? If A occurs doesn't depend on whether B has occurred or not, I could replace this left-hand side with just the probability of A. I could write that as the probability of A. So if independent, okay. And then I would say over on the left-hand side, that's the chance of A and B both occurring over the probability of B occurring. But then I'm sort of left with the opportunity to multiply both sides by the chance of B. And I'd say the chance of A and B both occurring is just the probability that A occurs times the probability that B occurs. Independent events have this characteristic that, yeah, I could multiply out the chances. It doesn't need a conditional statement. Any questions about the general rule? Okay, so what I'd love to do is to do sort of a cool example. And I guess the way our book way phrase it is in terms of there's a plane flying past, it's a bomber flying past a series of radar detectors, and do you spot the plane or not? And the radar detectors independently are able to see the plane or not see the plane. Okay, I want to change that up to correspond to something that I was working on with a faculty member in the packaging department of all things. And it's sort of a cool little problem. And the problem is basically, what's the chance that you miss your package if it's going through a set of scanners in a row? Now, I don't know that things work this way with Amazon anymore, but it used to be the case that they put these little RFID tags inside of the cardboard boxes right along the seat. And you should be able to spot this package because there's this little thing that's responding to the scanner and it says, oh, hey, I'm over here. And so you get information about whether the scanner has seen it or not. Okay. And so let's draw a schematic of the way the thing works here. We're going down this pathway here. Here a little box. Maybe I'll draw the box there. And this box is moving forward through the process. And there we go. Now it's actually looking more like a box. And as it goes through a series of archways, okay, each of the archways has a scanner, an RFID scanner in it. And the scanner should detect with a certain pretty high probability whether the package has gone through the scanner or not. So it's on this what do you call those things? Not a treadmill, but it's on this conveyor belt. And the probability that you see it is 0.9 with each of the scanners. So each of the scanners has a 90% chance of spotting that the package has gone through. The question is, what's the chance that you spot it at least once across in this case, 4 scanners? The probability of you spot the package. I guess that's using the 1 minus rule. 1 minus the chance that you miss it at all 4 scanners. And the chance that we miss it at every single one of the 4 scanners, I'm going to write the chance that you miss. The probability that you miss is 0.1. The probability that you miss here is 0.1. The probability that you miss here is 0.1. And the probability that you miss here is also 0.1. So the chance that you spot it is 1 minus the chance that you miss it every single one of the 4 times. That's 0.1 to the 4th power, and that's tiny. We end up with 1 minus 0.0001. And so that's a 0.9999. Pretty good chance. So even if your scanners are only with a 90% chance of spotting the package, if you simply have enough of them, and if the scanners operate independently of each other, you're pretty likely to spot the product at some point in time along the conveyor belt. Any questions about the example?
What if the kind of thing that causes a scanner to fail is the same in all scanners?
Okay,
Like if
so
it's a certain
yeah.
case, if that makes sense.
So what you're saying is, what if the RFID tag was never inserted in the box,
Right.
or perhaps it's defective? This is not that situation. I'm glad you brought up the special case here to sort of emphasize, oh, we're not talking about that problem. I'm talking about a problem just due to the orientation of the package on the conveyor belt. It comes down and sometimes it's upside down, sometimes it's sideways. But the RFID scanner, because it's in this arch, and there's actually several of them on each of these arches, you have, in theory, a 90% chance at each of them, and they're operating independently of each other. But John, the way you brought up the question suggests, yes, my model that says each of them have a 90% chance might be wrong. And the model, if they're independent of each other, you also hinted at that, that's also perhaps incorrect. The reason I want to, well, okay, I'm going to run a little bit further with that. There were ads in the Silicon Valley area that Oracle put up saying, oh, yeah, in 500 years, our servers will still be working, something like that. And it was about their hot swapping servers, where, yeah, literally you could pull out this one server, a little Linux box, and it's a rack of 20 of them or something like that. And they said, oh, yeah, if one goes down, then you pull it out and you put in another one, and the other 19 pick up the load for a period of time. So it seems like it's a great idea. But yeah, you're pointing out, John, that maybe that independence isn't valid. That literally the chance of one of these computers in a rack goes down, that chance increases because the first one went down and the other 19 have to take over the load. And so if you get one going down, it increases the chance that the next one goes down. And if you got 2 down, the chance that a third will go down is going to get even higher. And so it's the burden on the additional remaining servers. That's the issue. Oracle didn't really pay me money to comment on their ads, though, so I get to do it here for you. So, John, did I basically say in a way that you're happy with, yeah, this mathematical model doesn't handle that case, which is a realistic possibility?
Yep.
Okay. Anyone want to ask another question about it?
Can you explain why you subtracted 1 minus the probability that it
Okay.
misses all of them?
Okay, yeah. So what I was doing is utilizing a few of the rules here, and maybe I should go more step by step. So the chance that you spot the package, right, at some point in time across the 4 different arches is one minus the logical opposite is that we miss it every single time. So the chance of missing it 4 times in a row, well, that's subtracted for one to get the chance that we spot the package. So that's the one part of the one minus. So we got the sort of like so far the one minus part, but the missing it 4 times in a row, that means we have to miss it the first time, and we have to miss it the second time, and we have to miss it the third time, and we have to miss it the fourth time. And that's where I use the multiplication rule for these independent events and just have the 0.1 times 0.1 times 0.1 times 0.1. If we had done a tree, we're going to sort of spot it, or we're going to miss it. And then if we miss it, we're going to spot it or miss it, and spot or miss, and then finally spot or miss. And the miss case is what we're talking about. And the fact that they happen to be independent means you just multiply out those probabilities. You don't have to worry about the conditioning. So does that answer your question?
Yeah, it does. Thank you.
Okay. Want to follow it up? Or anyone want to follow up with another question on this example? Okay, so what I'll do then is clear this screen, and then we're going to talk about uh, the definition of a random variable. So let's talk conceptually first. So if you take an event, a random event, yeah, we're just saying something in the sample space has happened. A random variable really says the something that happens will get you a number. So here's the way to think about a random variable. We've got a sample space. Okay. And from the sample space, something occurs. Yes. So an event occurs, and it's going to be E1 or E2 or E3 up through E of cap N. Again, that's presuming there's a finite number of events, but we could rephrase it, supposing there's an infinite number of events. But the random variable part is not that. The random variable part is the next part where the individual E will get you to a number. So X is a random variable, yeah, if it takes a simple events, MPLE events, into a set of numbers. Okay, so basically, we've already talked about random variables, but we sort of did it loosely a week or two ago. You tell me something like this. I'm going to shuffle the cards off the top of shuffle a deck of a fair deck of cards. There's 52 in them, and I'm going to tell you X, and X is either a 1 if you get an ace, a 2 if you get a 2, a 3 if you get a 3, a 4 if you get a 4, all the way up through a 10. Well, that's sort of obvious. But if you get a jack, a queen, or a king, I'm going to give you 15. That's just a random variable. X is just a process for getting the number. The random variable literally is a way of mapping the items in your sample space into a collection of possible numbers. Okay. And so let's talk about an example of this that I think is sort of a fun one. I'm going to flip a coin until I get a heads. And so here's the items in the sample space. I'm going to drop pretty darn big. And I'm going to either get a heads first thing, or perhaps I get a tails followed by a head, or maybe a tail followed by a tail followed by a head, or it's a tail followed by a tail followed by a tail followed by a head, or tail, 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 heads, or tail, 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 heads, or, and you see the pattern. This is the sample space, the number of possible occurrences. There's an infinite number of possible items in the sample space. You know, it's just we're going to flip the coin until we get heads, and this is just the way that it could occur. And if X is equal to the number of flips, then X is a random variable, RV for random variable. So if you tell me here's an experiment and a way of getting an event, okay, and if you list off all the simple events and can tell me the way that the simple events convert into numbers, the outcome number is a random variable. So here's another example of a random variable. If I've got a normal population, I could take a sample from the normal population. So grab an X from a normal population with mean mu and variance sigma squared. For example, if X is distributed normally with mean 100 and IQs tend to have a standard deviation of 16, so I'm going to write 16 squared. If you define the mean in the standard deviation and then square it, you got the mean and the variance. What we're saying is any number in the range from negative to positive infinity could occur. And some of you are saying, well, that's not realistic. IQs never get negative. But this is what the thing says. If we say normal distribution, I'm just telling you all those possible values are equally are possible. But the distribution tells us how likely any given value is to occur. And I'm just going to pick one of those things from the normal distribution. Okay. So that's going to be a random variable. Any questions about the definition of a random variable? Okay, there are some famous ones that I'll talk about that you already know the name of. Would you believe that Poisson is a random variable, not just a probability distribution? So if the probability that X is less than or equals lowercase x corresponds to e to the minus lambda, lambda to the x power over x factorial for x is equal to, or I guess I shouldn't say it that way, for x's that are 0, 1, 2, 3, etc. And 0 is the chance OW for otherwise. If x follows that distribution, we say x is X is a Poisson RV. So our book did a lot of front loading. We defined these probability distributions. We didn't really call them probability distributions in terms of random variables, but they basically are, you tell me the list of all the possible outcomes and the chance of each, that is a probability distribution. So there's a few that we work with a fair amount. One thing, though, that we have with probability distributions and random variables is the opportunity to consider questions that relate statistics to probability. And what I mean by that is sample statistics to probability. And that will allow us to do what we are going to call statistical inference in chapters approximately 6, but certainly 7 and later. Okay. So if we have distributions about the population, there's a distribution of values in the population that could occur. And you're going to get a collection of data from the population X1, X2, X3, all the way up through Xn. You might want to summarize those data in a couple ways. One of them is maybe the sample mean X bar or the sample standard deviation S. Those are just two summaries of data. And if we are using fair and representative simple random sampling, we know that X bar tends to be related to mu, the population mean. In other words, the sample mean is going to depend on, in some sense, the population mean. And maybe the sample standard deviation would be related to sigma, the population standard deviation. If you tell me about the population you're sampling from, I could tell you what a collection of data would look like, at least in summary. Okay, so the idea here is this is probability. Probability tells us about possible X bars, possible X S's. So probability tells us the sampling distribution of sample means that could occur and sample standard deviations that could occur. We will later learn, based on these rules of probability that we're discussing starting today, how to infer I'm going to call it inference on mu and sigma. So if you tell me the sample mean, I could learn and say, oh yeah, the sample mean is probably close to the mean of the population. And I could even put a margin of error on the population mean based on the sample mean and sample standard deviation. And if you tell me the sample standard deviation, I could probably infer something about the unknown population mean. Usually in this class, if it's probability, we'll tell you things about mu and about sigma. If it's statistics at the tail end of the class, we're going to say, we don't know mu, we don't know sigma, but we want to learn about mu and sigma from the data in our sample, and characteristics in the data, things like the mean in the data, should reflect the mean in the population, or the standard deviation of the data should reflect the standard deviation in the population. And we already saw that in one of the labs. Sorry, I erased that too quickly. Do any of you have a question about that? Okay, so what I want to do is walk you through an example or two, and I'm going to sort of start with an example that some my colleagues wrote, and I'm going to hope that I get to remember the name of the it's down here. So Rossman Chance. So two colleagues of mine wrote a collection of these applets to learn about, okay, probability and statistics. And the one that I like to use is always moving around a little bit. Okay, so I'm going to go with, let's go with Reese's Pieces for fun. Nah, I'm going to back out of that one. I'm going to sort of go into this sampling words because it relates to sampling from a okay, hold on. Okay, I'm just going to go with sampling. I'm going to go with Reese's Pieces. Okay, yeah. I'm sorry about that. So we all know the candy Reese's Pieces, and if you go to the website for the company, they'll tell you orange happens 50% of the time. So let's just assume that's true. And let's suppose you have a quarter, you toss it in one of those machines at the grocery store, and you turn the crank. I'm going to show the animation because it's fun. And we're just going to count up the number of oranges we get. Oh, look, we got 10 oranges of the 25 candies in total. I got indeed 40% orange. And so I just dropped that number of orange down here. That's 10 oranges of the 25 candies. I could also display it as what proportion is 40%. I'm going to go with the number of oranges for now. We could do it again. Your friend has a quarter, puts it in the machine, turns the crank, and your friend gets not 10, but only 8 candies that are orange of the 25. And so your friend gets 8. Or if we switch over to proportion, your friend had about 30%. Actually, 8 of 25 is not exactly 30, but I'm having trouble dividing my head. You can do it probably more easily than I can because I've got a lecture buzz. So we've got this ability to sample over and over and over again. And rather than doing it in infinite number of times, because that's the way we have to do probabilities, is to try something an infinite number of times, I'm going to try it again and I get 32%. Oh yeah, that's exactly 8 of 25 is 30%, no problem. And rather than doing that a lot of times and show you every time, I'm going to go just for two more, just to show you that, yeah, indeed, we could just try not just one sample, but yeah, yet another one. And so we got another couple data points added in. Okay, so we've got 5 in total. I'm going to ignore the animation thing, and I'm going to draw, instead of 2 samples, I'm going to draw 5. And the nice thing is it'll do it all at once. I got another 5. And this is just the most recent time where I got 60% orange. So I got 10 in total. Okay. What if I was going to go with a whole, well, 90 more? That would get me to a total of 100. And let's grab 100 more samples. And it's sort of pretty quickly we get this information. Now we've got 100 in total. Let's go for another 100 at a time and go for 100, 200, 3, 4, 5, 6, 7, 8, 900. Maybe let's go for a full on 1,000. And you're saying, well, dude, this is just a binomial distribution here. But if we calculate as the proportion of orange, we could say this is a distribution of the chance or the proportion of orange I'm going to get in my sample. Indeed, what I have here is just 1,000 realizations of the random variable. The random variable is pull 25 candies out of this machine, and we're doing it with replacement. And after you pull the 25 candies out of the machine, calculate a chance or a rate, better yet, a rate of orange. In this case, we got 40 in the most recent sample, and just plot the distribution. This is a probability distribution for a random variable. Literally, my number p hat, the sample proportion of heads, is a random variable. A random variable, what is it? It's a number which is the result of a chance process that it's a number, and I can't predict it in advance. And so the process is grab 25 Reese's Pieces candies, calculate the proportion of orange. And we have a pretty good idea from our sampling distribution. This is the distribution of what happened. Indeed, we have a pretty good idea of maybe this is about what we're going to see if we do another 1,000. So for fun, let's do another 1,000. It's not going to probably change dramatically. Let's go for another couple thousand. When I see this result 10,000 times, that gives me a pretty good idea that this is the actual underlying shape of the chance of orange being, the proportion of orange being 30%. I could calculate that chance from my sample. Okay, so that's one example. I wanted to sort of switch gears and get you set up for something in the lab. And that is, I'm going to open up GMP, and the lab incorrectly, because we switched over to a different version of GMP from when I wrote the lab instructions, and I didn't discover this until just frickin' 5 minutes before class started. So I didn't rewrite the lab yet. I will be doing that shortly, and I'll upload a variant of that. If you want to wait half an hour before starting the lab, you should have the corrected version there. But I want to show you how to do it. If you've got JMP open, one thing I can spot is over here where it says help. Yeah, help. Just go down to not sample index, but instead scripting index. Yeah, scripting index. And I'm going to get a lot of things here. And darn it, did I do this wrong again? I'm sorry. Under help, not sample index. That's what I meant. Okay, where is it appear? Yeah, so so sample index. Again, under help, go to sample index, not sample data folder, not scripting index, but sample index. And then in sample index, click on where it says tool, and then search for the right tool. And the right tool is going to be down near the bottom, and I'm going to just go with sampling. Just type it. I'm just typing sampling. So sampling distribution of sample means.jsl for the JMP scripting language. So sampling distribution of sample means. Firing, clicking open. Come on. And it will show you something like this. Literally, if I'm sampling from a population like IQs with a mean of 100 and a standard deviation of 15, yeah, if I'm going to sample from that distribution 25 times, and I'm going to do that whole sampling process once, and sure, fine, go ahead, do the illustration or illustration, yeah. And I'm not going to plot the normal curve at first, but I'm going to draw a sample. Well, draw a sample. So if I'm sampling from a population of IQs, if IQs were normal following a mean of 100, standard deviation of 15, then in my first sample, I'm going to have someone who's pretty on the slow side, someone who's really pretty smart, and a variety of typical people out there. And if we were to calculate across my sample of 25, the average in this case was like 100.1102. And the standard deviation I got my sample was 13.9. If I were to do this again, draw an additional sample, the next sample from my population of IQs has a mean of 101.2766, a little bit different, a little bit higher. But here's the distribution. One is really on the slow side and one who's pretty smart. And we have the opportunity to do it again and again and again. I'm not adjusting the sample size, but I'm saying the sample size is here of size 25. Let's do, we've already done 2. Let's go for another 98 all at once. And because I don't want that to be clogging things up, I'm just not going to illustrate it. We're just going to get another 98. And so we're oh, that last sample is really pretty trippy because look, that is sampled from a normal population, but it looks in the sample pretty non-normal. But the sample mean is like 101, and I see, yeah, indeed, a distribution of the possible sample means. Yes, this is a distribution of the possible X bars. And let's even go for another 100 of those. And shoot, we've got now like 1,000 about. Here's 1,000 separate sample means that we've collected. And if I show you a normal quantile plot, you'd say, that looks really quite straight. So in other words, the distribution of the sample mean from this normal population is really quite close to perfectly straight. Very close to perfectly straight. So it does suggest something. And let's give you sort of a thing to write down. If you're sampling from a normal population, so if the population is normal, with mean mu and variance sigma squared, okay, then the distribution of the possible X bars will itself follow a normal curve, okay? So the distribution of possible X bars. So there's a lot of possible X bars that could occur, but I'm just saying they are themselves normal in shape. Okay, so cool. You're happy about that. I'm going to sort of switch gears back here and say, what else can we learn from this? Well, this is just with a simple situation where we had IQs, mean 100, varying, I guess, standard deviation of 15. What if instead of a sample of 25 individuals, what if we saw a sample of like 100 of them? Okay. I'm going to draw some samples. Another boom, 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 boom. 1,000. It looks as though my sample means they're really quite close to 100. They used to be further spread out. The standard deviation of the distribution of the possible sample means is a lot smaller now. So let's formalize that just a little bit. Okay. So if we're sampling from a normal population, okay, so if the population is itself normal with mean mu and variance sigma squared, the distribution of the possible X bars, and I guess I'm going to collect data and then get an X bar, is itself normal with mean mu and with standard deviation equal to the standard deviation of the population you sampled from over the root of the sample size, root of n. And because we're seeing, instead of a sample of 25, a sample of like 100, you're thinking 100 is 4 times 25. The standard deviation should be cut in half. We have double the precision because of our new larger sample size. Every time we quadruple the number of data points that we're sampling, okay, the distribution of the possible sample means is half as wide as it used to be in terms of the standard deviation. Any questions about that? Okay, so that's one thing I suggested. What about other situations? If you're not sampling from a normal population, you might very well be sampling, and this is something that I think we asked you to do. Actually, let's go with pennies. Mhm. Okay, come on. Oh, it says not secure, damn it. Okay, so let's try this, and we're gonna hope. Okay, so if we're gonna sample from which distribution, pennies, I'm gonna go with that. This is a distribution of the age and variable. There we go. Use data. There we go. So here's the distribution of the age of the I guess the year on the penny. Okay. So I guess at one point in time, we asked a collection of students to bring in pennies, and 1,000 pennies were brought in, and we just asked everyone to look on the penny and what year is it? Oh, it was 1995. So we wrote down 95, or 1970. So we wrote down 70. Here's the distribution of the actual years on which the penny said. And so if we're going to sample from that population, that's certainly not a normal population. And if I were to sample, let's try one time at first, and let's sample, say, 4 pennies. Okay. And I'm going to collect 4 of the 1,000. And I got like 84, 77, 76, 96. Okay. And so the ages, because it was 99 that we collected the data, are 15, 22, 23, and 3 years of age. And I'm just calculating the average of the ages here, or the average of the years. It's really the same thing. I'm going to work in terms of years. Here is the 3 years that we saw. There's the 76, 77, 84, and 96. They gave me an average of 83.25. Okay. And I'm going to draw another sample. We get another collection of years, 81, 84, 83, 98. Those the 81, 83, 84, 98. The average of these 3 pennies ages was 86.5. I'm going to plop it over here. And rather than doing just one sample and doing that 100 times, well, one at a time, I'm just going to go for another 98 all at once. Now we're at a total of 100 samples, and this is the distribution of the possible sample averages. And let's go with another 100 all at once. And let's go for a lot of those. Oh, we've got now 1,000 samples of 4 pennies. You and your 999 best friends all say, let's go grab 4 pennies. And you reach in your pocket and you tell me, here's the ages. You did this in 1999, by the way. And this last person in your sample, your 1,000th best friend, had those 1, 2, 3, 4 values, which seem to be fleshing out the distribution of the population that we're sampling from pretty well. And they give us a sample mean, and I plotted it here. And this distribution of the possible sample means shows me what could indeed happen if you're sampling from this exact population 4 times. So I'm going to try, instead of 4 times, what if instead of 4, we're going to go with 16? Notice here that across my my sample means, the standard deviation here is about 4.5. Remember that 4.5. The claim was earlier, maybe if I were to quadruple the sample size, the spread of the possible sample means should be cut in half. I'm going to reset that and draw samples. Now I've got 16 sampled individuals. again, fleshing out the histogram of the population I'm sampling from pretty well. And I get a sample average. I'm going to plop it up here, and I got 100 of them. Let's do another 900 to 1,000 total. I'm spotting a couple things. One is it's still centered at about the same place, about 86, 87, which is where the population mean was anyway. And secondarily, the standard deviation now, instead of like 4.5, is like 2.3. So the standard deviation was cut in half by quadrupling the sample size. I also am spotting when I had 4 as my sample size, it did seem a little skewed. A little less skewed now that we have 16. What if we had a sample of, say, let's go with another 4 times that, 64. Reset that, and I'm going to get a collection of 64, and I'm going to do that the 1,000 times. But in my last 64, sample of 64 from the distribution of ages, we see very well fleshed out in the population histogram. We see a whole bunch of them as having been chosen. Here's my sample histogram, which seems to even have almost the same shape. This bimodal shape in the sample histogram is reflecting a bimodal shape in the population. And my sample means, the last one was like 85.9. On average, we're like 86.7, which was the mean of the population from which we've sampled. Oh, and look at that. That also looks as though it's pretty darn normal in shape. And what I'm spotting is the distribution, the possible sample means, is sometimes normal. Sometimes it's not normal in shape. Let's close out by saying, here are the conditions in which the distribution of the possible sample means will follow a normal curve. So the sampling distribution, let me just write that out better. Of the sample mean X bar is normal mean mu variance sigma squared over n. Okay, right, yeah, variance mean. If the population is normal. Okay, and second, the sampling distribution of X bar, well, if the population isn't normal, we'll still have mean mu and variance sigma squared over n. Okay, that's if its population isn't normal. But here's the third thing, the fun thing, is approximately. Mean mu variance sigma squared over n. If the population isn't normal, okay, population isn't normal, but the sample size is big enough. By big enough, I'm going to sort of close it out by saying, you know what? Stat books, we have always this challenge of, okay, we teach you a rule, and then we say, here's a rule that's real and true, and it applies in situations like this. The sample is big. You know, you're wondering how big. Well, we can't really tell you exactly. What we can tell you is closer to normal, the larger n is. That's a for sure. The distribution of the possible sample means will be closer and closer and closer to following a perfect normal curve, the larger and larger and larger the sample size is. So you'd be happy with a really large sample. But what if your sample is only like 25 or 40? Is that big enough? And we're going to say, in practical terms, what we typically see is a sample size of 25 or 30 is big enough. that the distribution of the possible sample means will be close to normal. But I could generate for you an example where even a sample of 100 wouldn't be large enough for us to say, aha, the distribution of the possible sample means the possible X bars is normal. I could generate that. We're just saying that rarely happens. I will just say for most any normal, shouldn't use that word, for any population that I typically see in real life, a sample of 30 or so is sufficient. And so with that in mind, the lab today, I have to fix the instructions for how to get the app to work, JMP to do what I want you to have you do. You might remember, I'm going to walk you through it one more time right now. If you're going to go and do the lab right away, just you have to replace those instructions. So here's how to do it yet again. So under window, no, sorry, under help, yeah, under help, say sample index. And then once you have the sample index, you're going to have a lot of different possible samples. Instead of data, go with tool, okay? And geez, that's a lot of them. Just start typing SAMP for sampling distribution. You're going to find the sampling distribution of sample means. That's the one you ought to be using. And just click OK, open, and it should be absolutely fine. Okay. So you could go with normal population, you could go skewed right uniform or your own data. And if you do your own data like the lab asks, you click that and it'll say, what data set do you want? Well, you have to have the data set open. A data set that I have open gives me choices of variables to sample from. You will have already opened the data you want, and you should be good to go at that point in time. Okay, we're at a good place for me to close it down and say thank you for your patience. I appreciate it. And I'm going to stop the screen share here. Pause for a little bit for questions if there are any, and then I'm going to stop the recording. And then I'll be in office hours at 7:10. I'm sorry, 5:10, different time zone. I think about it differently. Any questions right now? So I'm going to stop. Oh, John?
I have a question that's
Sure.
stats related, but not class related. So if
Okay.
anyone else can ask first.
Yeah, I'll stop the recording if no one else has a question first. And they're disappearing quickly, so I'm just going to go ahead and stop it.